learning this or any monotone conjunction using this protocol of active learning is the number of features, is the dimensionality of the problem. Questions about this? Yes?
Could you explain again how you got x100 is in X and x100?
Right, so let me just go back to that. So this question, right? So consider, quick logistical thing, is the video working now?
Yeah.
Oh, excellent, thanks. Thanks. So consider the case, let's take a simpler function. Instead of x100, let's say we have only 3 variables. Okay? So let's say the function f is x1 and x3. So the function takes the value 1 if and only if all these things are present, and it takes a value 0 if any of these are absent. So now I'm going to pose the query 1. So I have 3 variables, so x1, x2, and x3. I'm going to pose the query 1, 1, 0. Now, suppose you did not know this function.
Oh, okay, yeah.
Suppose you did not know this function, but you do know that this takes the value 1. If it takes the value 1, that means that x3 was not needed to make the function 1. So x3 is really not present, and the only reason we know that is because it's a monotone function. Suppose it takes the value 0. That means removing only x3 forces the function to become false, which means x3 is an integral part of the function, which means x3, I don't know what else is present, but x3 is definitely there. And that query basically conclusively proves in some sense that x3 is in the function. Other questions? Give me 1 minute. Yes. Yeah. Was there other question? Any other hand when I was looking up? Yes.
So this algorithm or this approach assumes that we know it's a monotone conjunction.
Yep.
How do we figure that out?
We don't. This is a lot of the. This is a good question. In real life, we hardly ever know that. In a lot of the learning theory kind of examples, we will assume that the concept is in this class of functions, and then we can ask the question: what is the difficulty of learning this concept? What I just answered here is the answer to the question of what is the difficulty of learning monotone conjunctions under active learning. And the difficulty is the dimensionality of the problem. If there are 100 features, you need 100 queries. So, of course, then there's the question, what if you know that the function is a conjunction but not necessarily monotone? Remember, we use the fact that it was monotone quite extensively. It turns out that if you knew one positive example, then we can kind of make things work. I'm going to leave this as an exercise, and this is just a hint at the answers. We can, a similar sort of approach, you need to invent a new protocol. And that will work for non-monotone conjunctions also. Non-monotone conjunctions are conjunctions where you allow some things to be negated. Okay, so that's protocol 1. Now consider protocol 2. Remember, in protocol 2, there's a teacher who gets to choose examples. The teacher picks examples and says, here, these are the only examples you need to learn the function. That's a very important piece of information. If I know that these are the only examples needed to learn the function, that means that already leaks some information about the function. In the same way as in an exam or a class, I know that your search space, so if let's say you see a question in an exam, and the exam is set in a somewhat reasonable way, you know that the answer to that question is in something that was in the syllabus, right? It's only in the syllabus and not something about, in the machine learning class, I wouldn't be asking you questions about compilers. And you know that. That restricts your search space in some sense. So this sort of information is crucial and it can be used by the learner. So let's see what happens with the teaching protocol. The first thing that the teacher could do is to convey to the learner a superset of all the good features. So it says, x2, x3, x4, x5 and x100 are, at least these things are needed. And the way it proves it is to show one example, a positive example that has these 6 things on and everything else is off. All the learner knows at the end of this is the true set of variables is a subset of these 6 things or 5 things. Right? All I know at the end of seeing this one example is that the true conjunction can be f could be x2 or f could be x2 and x5 or any of these things, because all of these functions would set that example to be true. Next, it needs to prove that every one of these variables are needed. So this shows that these variables are sufficient. Next, it needs to show that every one of these things are necessary. And the way it would do that, it would give 5 more examples. It would show that x2 is necessary by turning off x2 from that original example, and the value becomes 0. This means that if you comparing these two things, removing x2 changes the value of the function, so x2 is a necessary part of the thing. The next one, it turns off, the teacher would turn off x3, and comparing the original example and the most recent one, turning off x3 makes the function value 0. So the notation I'm using is example, comma, label with an angle bracket, so the function value becomes 0, and that means x3 is needed. Yes?
Is this not the same sort of algorithm you would do with what you were talking about in protocol 1 if you had one positive example?
Almost, yes. In fact, almost, except once you had one positive example, the learner would be posing these questions.
Okay.
Yeah. But then you have to the learner has to first discover that positive example. And that can take a fair number. So, essentially, for every feature that is present in the conjunction, you need one query to prove that it's required. And then you need one more query at the beginning, not a query, one more labeled example at the beginning that shows these are the only things that are required. So, what happens is, this takes the form of necessary and sufficient kind of proof. The top example shows that these variables are sufficient, and then the bottom 5 things shows that these 5 variables are necessary, and that's essentially a proof that these are the only 5 variables that are in the function. Questions? And at this point, with these 6 queries, you know the function because this one should, and so on. And so you know that it's a subset of those 5 things, and every one of those 5 are needed. So teaching is extremely efficient in terms of the number of examples needed, while active learning required an entire 100 examples. Teaching requires only 6, and this is the intuition that a good teacher can do a good job. So, yes.
Is the 6th example?
The bottommost one?
Oh,
This one?
yeah, or, okay. Well, if there's 5 variables, doesn't it only need 5 examples?
Oh, you need 6 because you need to show that all of these are needed. Because you see how, I see where you're going. Your question is, aren't these 5 enough?
Yeah.
If the top one needed. I think why you need the top one is because you need to show that these are the only things needed and nothing else. So because there are so many zeros here.
Okay.
So you need to know exactly if this one that's needed. So that's a good point, right? I mean, this particular example does not say whether it's x2 or x1 or whatever those other things that are causing the function to be false. You and then, I've heard your voice before, so I'm going to go there first.
Could you also just have all ones except for the x2 be 0? Like, does it have to show zeros and ones that don't matter?
Yeah, so there are some games to be played here. Yes, I think that might work in this case. I have to think a little bit more. It might, but you'll essentially maybe gain one more out of that. That goes back to the earlier question that was asked. Yes.
Sorry, so this is kind of on this similar, but so could you get one example, since you know that you have this contract that the learner knows, the teacher knows that it's going to give it the right input.
Right.
So could the teacher pass it one example with all the right bits set to one, and that's just one example?
That's the first one.
But that has arbitrary bits set as well, right?
No, it has exactly those 5 bits set to 1 and nothing else. It has exactly those 5 bits set to 1, but at the end of that example, the learner still cannot know that there's no agreement between the learner and the teacher upfront that the teacher will transmit the function. The teacher only transmits examples. Despite what you could think of as an adversarial setup, you need only a small number of examples. That's the point. I mean, you can of course change the protocol a bit one way or another to kind of make it even more efficient. Like if the teacher and the learner have extra information that the learner is convinced that the teacher is going to try to convey the example using one example, convey the function using one example, maybe the first one is enough. But I'm assuming that there's no such contract up front. But even in the absence of such contract, you need only 6 examples. So the point here is teaching can be extremely efficient, and unfortunately, teaching is extremely hard to model, so we'll never see this again. Let's go to the third protocol, which is the more realistic one, and that's the protocol that we'll be looking at pretty much for the entire semester. This is supervised learning. There is some random source that picks examples. Neither the learner nor the teacher get to control which examples are labeled. Some random set of examples are labeled. And the labeling is of course done by the teacher using the true function, but in this case notice that the teacher does not have much of the job. All it has to do is wait for nature to pick the random examples and apply the function, and then walk away. So let's say in this example there are these whatever number of 10-ish, maybe 10 or 8 or 10 examples that the learner gets. Now the question is, how can we learn? So first of all, and I'm going to walk you through a learning algorithm that you can learn because this is the monotone conjunction. This algorithm, we're going to call it the elimination algorithm. What you do is you get a collection of examples that are randomly chosen. Some of them could be positive and some of them could be negative. What you do is you first delete all the negative examples because we're not going to reuse them. So I've just muted their color. So in this case, we are left with 4 positive examples, and all we need is to know that this is a positive. So this example here is positive. That means the true some subset of these features is the true function. This example is positive. That means some subset of these, the ones, should be present in the true function. And essentially, every positive example eliminates a collection of features. For example, this positive example eliminates this feature. The positive example says, I don't know what the true function is, but this particular feature should not have been in the true function because look, the function value is still positive and that feature is 0. So I don't care what the true function is, but feature number x99 is absent. And similarly, every positive example eliminates a collection of features, and the features that remain is essentially the intersection of all the ones that in the positive example. So that means that what we get is we know that x100 is present because every positive example has it. We know that x2 is present because every positive example has it, and that gives us x2, x100. And notice that we have this one extra variable, x1. Because the examples were randomly chosen, it so happened that x1 happened to be present in all the positive examples. It didn't hurt the function, it does not make the function wrong, but x1 happens to be present in all the positive examples, and this elimination algorithm has no way of knowing that x1 is not in the true function. Any questions? about the algorithm or the statement that I just made, that there is no way to know that x1 is not in the function. Yes?
So in protocol 3 or supervised learning in general, the learner can't ask for a specific example.
It cannot. The learner does not get to make any question, ask any questions.
But if it could, after the first example, you could just run 100
Yes.
questions and find.
That's absolutely right. If the learner gets to ask questions, learning becomes more efficient. If the teacher gets to pick examples, learning becomes more efficient. Here, we are left with what we have. Yes.
So I have two questions. The first question, what do you mean by x1 is not present?
Oh, what I mean is the true function did not have x1.
So the second question, isn't this what we have been doing? Like we give us a truth table with the function and we have to figure out what is the function exactly?
That's right. This is not just what we've been doing, this is what we... Wait, can you repeat the last part of what you asked?
So you give us a truth table with the values for the features
Right.
and value for the function, we have to figure it out.
Yeah, okay, that's one. Yeah, but I don't give you the entire truth table, I give you a very small subset of it. Yes, that's right. And in addition to that, I'm not saying that there's one more twist here, which is I'm telling you up front, or the teacher is telling you up front, that the true function is just a monotone conjunction. It's not any Boolean function, you just need to find a monotone conjunction. Yeah.
Could we use the examples for false label, not in this particular, but in general?
You could, of course.
To specify the function further.
You could, but in this case it doesn't matter. In general, of course, I mean, you could use all the data however you want. In this case, it's not going to matter. But yeah, in general, yes. Yes.
So in this case, we're taking the perspective from the teacher, so we already know the true population.
The teacher does not know anything in this case. The only thing that the teacher knows is the function.
But
Yeah.
we assume, okay, but we assume the function is what we're looking for.
Yes.
Okay.
Yes. The goal is the learner has to somehow get the function at the end of this interaction.
And what we did previously was we were doing from the learner.
What do you mean?
We were asking the question and predicting whether our prediction was close.
Well, in all cases, the overall setup was there is a teacher, and the teacher has a function, and there is a learner, and the learner does not have a function, and the goal is to somehow transmit that information, one way or another. And if you think of learning as the process of transmitting information from the teacher to the learner, you can set this up in multiple ways, and the question is who initiates the process. I mean, or rather, who picks the examples that are being labeled. The information is being transmitted not by just writing down a function and giving it, but by transmitting examples only. In all cases, it's transmitting examples, and the only difference is who chooses those examples. There was a hand there.
After getting we are checking for the positive values, right?
Yes.
So we know it's a monotone convention.
Yes.
So can the learner ask questions to cross-verify if
That was related to the earlier question. Perhaps it could, but we are living in this world today in the protocol 3 where the learner is not allowed.
because we have some false examples.
Yes.
And we can use
Perhaps.
x1 in the last example is 0
Yes.
and the label is 0.
Yes.
Essentially learner can use that example
To
eliminate x1.
You cannot, right? Because the label is 0. All this tells us is that something is, one of the true variables is missing. We don't know which of the true variables is missing. And notice that in this case, I think maybe I was cleverer than I had intended. X3 is also missing. So we don't know which of these is causing the function to be false. There was another question. Okay.
So it seems that many machine learning applications involve automation of something humans can do, etc., like that.
Right.
But it seems like Protocol 3's fall is a majority of what people think about machine learning
Right.
and active learning.
Yes.
Why is that? Even though
Because it's easy for us to implement, write down algorithms of this kind. Active learning is particularly difficult to set up in an experimental point of view, for example. Because in active learning, you probably learned it. Imagine that I have to learn what it means to be a cat. I use cats because it's particularly a difficult concept for, it used to be a difficult concept for programs, but not for humans. So, active learning, if I can demonstrate, give you a program that uses active learning to learn a cat detector, all I have shown is that I have demonstrated a program that uses this sequence of examples to learn a cat detector. Maybe if I had changed the sequence, I could have done better or worse. So there are some experimental issues with setting things up that way. The second thing is, from a practical point of view, this learning labeling examples has proven to be, at least for a lot of tasks, has proven to be not too terribly difficult. You can always pay people. So if you have a lot of money, you can kind of get around this problem. The third point that I wanted to make is it's not that it's never used. A mild variant of this idea of active learning, not a mild, a major variant, but one variant is reinforcement learning, where the learner performs an action, makes a decision, and that decision takes the learner to a new state, and now the learner enjoys the reward or gets some punishment. And the goal is to minimize punishment or maximize reward. And the learner's actions iteratively kind of improve its own concept, its own hypothesis. And that is quite extensively studied, for example, for robot learning, for instance. So it's not that it's not used. A lot of applications that we think of as standard machine learning, like the self-driving cars, not self-driving cars, these things that we talk to on the phone and all those things, tend to be supervised learning because they are powered by big companies which can actually collect the data. And then you can kind of, once you've collected the data, you can, tomorrow maybe somebody invents a new learning algorithm, you don't have to go and redo the data collection, you can just use the new algorithm on the old data and things like that. So it just has some convenience. Okay, so the other point I wanted to make is notice that whenever the output is 1, it just so happens that the variable x1 is present in that example. When I say variable present, I mean it takes the value 1. And this is an important point I'm going to make. Using this given data in protocol 3, we've not learned the true function. The true function was x2, x3, x4, x5, x100. We've learned x1, x2, x3, x4, x5, x100. It's not the true function, it's only an approximation of the true function. At this point, we have to ask, is this good enough? There are clearly examples where f, that's the true function, and x, that's learned, are going to disagree. And what can we do? Any thoughts?
More examples.
You can ask for more examples, but let's say we've exhausted our budget for examples. Can we live with this? Yes.
There's no way for us to know that our hypothesis is not correct without more examples.
That's right.
So it's whether it's good enough or not, you can't really judge it. It just is.
It is. That's true. So you live with it.
I guess depending on the application, how costly is a false negative? Because if
This will only make false negatives.
exactly.
Yes, you can get it down on the error rate.
You could. In fact, that's what we're going to try to do. In order to ask ourselves how good is our learning algorithm, there are a few different directions. We can analyze the following probabilistic intuition. It just so happened we exhausted our budget for collecting data, and we never saw x1 equals 0 with any positive examples. Maybe the way nature is set up, it's a very rare event that x1 will be 0 with positive examples, so we'll not make too many mistakes in the future. Because we drew examples from the distribution that nature supplied. And even in the future, when we will not have to make this error, we won't make this error because x1 will never show up with positive examples. Or even if it does, it would be rare. And as a result, our approximation is pretty good given this distribution of data. This intuition is the basis of what is called the PAC framework for machine learning. It's called the probabilistic, probably approximately correct framework. Another intuition is what we're going to look at now, which is instead of thinking of this one bucket of data given to us and we'll never have to ask for more examples, let's imagine that our learning algorithm lives in this iterative, it's a continuously learning thing. It's an algorithm that is given a collection of examples, it has a current hypothesis, and it makes decisions using this function as long as it exists. And at some point in the future, it may get a new example, and it's given the opportunity to update itself, and it keeps making predictions as it goes along. And the only thing that matters is that the function should not make too many mistakes over its lifetime in this sort of an online setting. And we can define good in terms of the function not making too many mistakes in the future. Not making any more mistakes. If we can somehow prove that the function will never make mistakes, life is good. And we're going to look at this intuition right now. This idea of this learner being in the stream of examples. Yes?
When you say online in the context of machine learning, what do you mean exactly?
It's a good segue because that's what we're going to do.
Okay.
We're going to look at what online learning is, and we've spent some time looking at online learning, and through this process I will introduce the perceptron algorithm. And once we're done with that, we'll go back to the PAC model and go back to the same question of how good is our learning algorithm. So, just to tell you where we are in the big picture, in the last lecture and the lecture before, we looked at linear models, and today we are looking at what is how good a learning algorithm is. One way of answering that question is using this framework of online learning, and marrying linear models with online learning gives us the perceptron algorithm, and if time permits, we'll also look at another really cool thing called the Winnow algorithm. Another way of answering the question of how good a learning algorithm is the PAC framework, or the framework of empirical risk minimization. Today, that's the dominant framework for designing learning algorithms. And this framework, combined with linear models, will give us support vector machines. And there is also other ways in which we can answer the same question. In particular, the one that we'll cover is Bayesian learning. When we marry that with linear models, we'll get logistic regression. So different learning algorithms are invented using a slightly different perspective on the same question of how do we know that learning is done. So let's look at mistake-driven learning, which is a special case of online learning, and then we look at learning algorithms under this mistake-driven framework for linear classifiers. One thing that I want you to keep an eye out for, even if I do not mention it, I want you to keep an eye out for this idea that the representation that we choose for learning is important. Remember that idea of blowing up feature spaces that I brought up? Maybe something is not a linear function in the original feature space, maybe it's linear in a high dimensional feature space, and how do we learn that in the online setting? And in general, keep the idea of the right representation in mind, because that makes or breaks learning. And that's something that I want you to have in the back of your mind at all points. Another point that's going to be important is the complexity of learning. We need to define the complexity of learning in a formal way. That could be in terms of the number of examples, it could be in terms of the quality of approximation of the true function, some combination of these two things. Just keep that thought in mind, and we will formalize these things, but I want you to keep the idea that we are trying to quantify the complexity of learning. So let's first look at online learning and more special version of that called the mistake-bound model. As a motivation, as an example problem, let me introduce a specific instance just to tell you that you can have it in your head. Suppose you have a learning problem with a very high dimensional feature space. Imagine that you have 1 million features, Did I put 1,000,000 or 100,000? It doesn't matter. A big number. Imagine that you have 1,000,000 features, and suppose the true function, we don't know what the true function is, but we have some reason to suspect that the true function is dependent on a very small number of these features that we have. So, does it make sense? I mean, we can keep inventing features, right? We have the luxury to keep inventing features, but the true function is a function of the true concept it depends only on a small number of these features. An example is there is a typo in this sentence. Can someone tell me what the typo is? Result. It should have two S's, but of course it's not a spelling mistake. It's a grammatical error. And you can tell that this is wrong because you're looking at the context and you know that there should be two S's there. So imagine that you trained a classifier for this problem that looks at a word and asks, is this the correct thing or not? And is this, or, I think I got that right. Maybe. Anyway, so you have this binary classification problem. Is it dessert or dessert? And I can invent features that are like, for this current target word, what is the indicator for is the previous word Eastern, is the previous word is the previous word cat, the entire vocabulary. And is the next word. And if your feature is the size of the vocabulary of the English dictionary, then you have a lot of features, but really most of them are irrelevant. So, can we, just a motivating thought that I would like you to have in mind is, can we develop a learning framework or a learning algorithm that depends only weakly on the dimensionality of the problem and mostly on the number of relevant features. In the more concrete example I have up there, we want a learning algorithm that can learn whose complexity, the time complexity of learning is a function of the number of relevant features, in this case 5, and it does not depend very strongly on the total dimensionality, which is 1,000,000, even though we don't know the true function. Yes?
I mean, one thing you could do here is restrict it from being the entire vocabulary to looking at the grammatical structure.
Sure, but you're changing the question.
Okay.
Right. But I could argue that even there, the dimensionality is very high because we'll take that offline. Grammatical structure could be a much higher dimensional thing. Let me introduce now. The reason I introduced that question is I want you to just keep that thought in mind. What we care about is a weak dependence on the true dimensionality and a dependence only on the number of relevant features. And this was a question that was, for some reason, a really pressing question in the mid to late 80s. Yeah?
So, we can see that this sentence does not make sense, but it can be a sentence that makes sense but is irrelevant.
Yes.
Yeah. So, should the classifier be negative result or stay irrelevant?
For now, it depends on how you want to set up the question. They are different learning problems. Those two things that you said are two different classifiers. So, depends on the application, depends on what you need in the application. Okay, so let's set up mistake model learning. Let's say that we have an instance space. As always, we are calling the instance space X, capital X. And let's say that the instances are n-dimensional examples. However you define the dimensionality, it could be Boolean or real or whatever. There is a target function f. F is a function that maps x to either true or false, 0 or 1. And let's say f belongs to the concept class. F belongs to a set called C. In the example that I had before, the concept class was monotone conjunctions. And let's say the size of the concept class is somehow parameterized by the number n, the dimensionality. And we'll see why that is so in a bit. The learning protocol, online learning, can be thought of as a continued series of games between the learner and let's say nature or teacher or whatever. The learner is a randomly chosen example X is presented to the learner. That's capital X here. And the learner has to first make a prediction. And the prediction is using some hypothesis that the learner has, it makes a prediction, h of x. After having made the prediction, the true label to that example is revealed. And now the learner has one more labeled example and it can choose to somehow correct itself. The performance that we are going to, that's it, that's the general essence of all online learning games. And the performance of the learner is quantified by the number of mistakes it makes. Essentially, the learner loses a point, or the learner gains the -1 point if each prediction was not equal to the feedback it received. So it makes a prediction, and then it gets feedback, and the true label is revealed, and if the true label was not equal to the prediction, then the learner loses a point. Otherwise, the learner continues. Is the setup, does this make sense? Before I start introducing some notation. Yeah?
So isn't the learner asking for instances here? So isn't this active learning?
No, the learner does not get to choose instances. In fact, the learner is given an instance that is randomly chosen.
Oh, it's just predicting the label.
Exactly. All that happens is the learner is given an instance, and given this instance, let's say I'm the learner. I have to make a prediction. And let's say you're the teacher here. I first tell you, nature gives me an example, I make a prediction. I say that this example is positive. At that point, you have the opportunity, or you are required to reveal the true label for that same example. And neither the learner nor the teacher get to pick examples. So, given this setup, clearly the performance of the learner depends on the sequence in which the examples are presented. Let's say we have a sequence of examples. Yes. Yeah.
How do you get permission for learners? I mean, how do you say it's a good learning or not?
It's a good.
Learning or not?
Yeah, that's exactly what I'm going to define next. So, all I have defined so far is that the learner has made a mistake on the example that you just saw. That one example. So we have a concrete definition of what it means to have made a mistake on one example. We're going to use that to build up to a sequence of examples and then the entire concept. So let's say we are given a sequence of examples. S could be something like a sequence x1, the first example that was shown, and then x2, these are all vectors, and then x3, and so on. And let's say we have a sequence of n examples. The learner gets to see a sequence of n examples, and the true function is f, always. And the learner uses some algorithm. Internally, it gets to, after this step, the learner gets to reset its state. It gets to choose a new hypothesis. And that procedure, let's call that algorithm A. The learning algorithm is A. So, given us a particular sequence of examples, we can count the number of mistakes that this protocol, this game, has made on the sequence for a particular function, right? So I'm going to define m sub a of f comma s to be the number of mistakes that algorithm A makes on a sequence S for the true function f. It's just the number of mistakes made when the true function is f, right? This is just this should not be a chattering definition. Now, I can now generalize this to the entire concept class. Now, suppose this is the mistakes, the MAFS is the number of mistakes made by the algorithm A for the function f on a particular sequence S. Now, suppose we have the entire concept class C that consists many functions. We don't know what the function is. Maybe some functions are easy and some functions are hard. So let's assume that we have the most difficult function in that. We can ask what is the number of mistakes made for a particular sequence on the most difficult function. Right? We could also ask what is the number of mistakes made by this algorithm on the most difficult function for the most difficult set of examples that were presented. Imagine that there's an adversary that's choosing the example. The sequence S is not being constructed randomly, but it's being constructed adversarially. It presents the worst set of examples in order to make the learner fail. So MA of C is the number of mistakes made by the maximum possible number of mistakes made by the algorithm on any target function for any sequence of examples. By any, what I mean is there's an adversary at play. The adversary chooses the hardest function and the hardest sequence of examples, and MA of C is the number of mistakes made on that particular sequence for that function. Questions? Yeah?
So is C the concept class like kind of what we were talking about earlier, like a set of like monotonic conjunctions?
That's exactly it.
Okay.
C is a set of functions that we believe, that let's say the learner believes, it contains the true function. It could be monotonic conjunctions, it could be linear classifiers, some class of functions. Yeah.
Do we have to run through every possible S to find S for the max C?
We don't have to. Let's assume that the adversary has infinite computation and manages to do it. We are assuming like a adversary that is extremely powerful, that manages to find the worst sequence for this learner. Yeah.
So is this analogous to just worst case performance for this learning algorithm?
It's worst case performance, but not time or space, but accuracy.
Okay.
But we're not defining accuracy, it's worst case number of mistakes. So we're going to define an algorithm to be a mistake-bound algorithm if even the worst case number of mistakes is polynomial in n, which is the dimensionality of the problem. It's just a name. So far, all I have done is defined a set of things. I've defined an algorithm to be a mistake-bound algorithm if even a mistake-bound algorithm for a concept class C if the most difficult function in the concept class and the most difficult sequence of examples causes this algorithm to make only a polynomial number of mistakes in the dimensionality, and essentially that's what we are going to define as learning. Any questions? And keep in mind at this point, all I have done is defined a learning algorithm to have a property. I have not even proved to you that there exists even one algorithm that has this property. Maybe I have defined, I can define whatever I want, right? I can define an algorithm that's a mistake-bound algorithm for the concept class if it makes 0 mistakes from start to end. Maybe I can do that, and maybe there are no such algorithms. I still haven't convinced you that there's even one such algorithm that exists. Right? I could have defined an empty set here. This is just a property of an algorithm. And one thing I'd like to point out is this is not the most general setting for online learning. There are, more commonly in the literature, you will see more general settings involving other metrics for quantifying performance. The most common one that's used in the literature is probably called regret. Regret is the idea that after having seen a collection of examples, the learner plays this game and it makes some mistakes, and it's not too much worse than the best thing it could have done in hindsight. And there are regret-bound algorithms, just like mistake-bound algorithms. So in this class, we're only going to look at mistake-bound, but if you're interested, you can look up regret-bound, and it's not the most difficult thing to understand, but let's start with the easy thing. Questions about this definition?
So, shouldn't we have the condition that all of the sequence of examples have the same length? In terms of that maximum argument there? Otherwise, you could just keep adding wrong answers and keep growing that maximum number of mistakes.
Unless it never makes mistakes.
Right, so it's either going to be countably infinite or 0. necessarily, right?
or small. It makes a bunch of mistakes and then never makes mistakes forever in the future. And in fact, the sequence could be infinite, and that's a subtle but important point. The sequence could be infinite, despite seeing an infinite number of examples, despite having this all-powerful adversary that's picking examples. A mistake-bound algorithm will never make mistakes after meeting this bound. And like I said, I haven't shown you that such algorithms exist, but of course, I mean, I would not be spending this time on it if they don't. The sequence could be infinite, and that's there's nothing in the definition that prevents it. So, one more definition before going to the actual thing. What I've written here in the top is just a restatement of what I just wrote. The algorithm is mistake bound if the maximum number of mistakes it makes for any sequence of examples is polynomial in the dimensionality. Now we can talk about concept classes. A concept class is said to be learnable under this model if you can show me one example that can learn it under this model with polynomial number of mistakes. If there's even one example, if there exists a mistake-bound algorithm for a concept class, then the entire concept class is said to be learnable. So now we can ask questions like, are monotone conjunctions learnable under the mistake-bound model? The meaning of that question is, does there exist one algorithm, a single algorithm, that can learn monotone conjunctions, making only a polynomial number of mistakes for any sequence of examples? And polynomial, keep in mind, polynomial is not a big deal. Sometimes when people say polynomial, you might think n squared, but n to the 2 is also a polynomial. Just keep that in mind. Polynomial is not the end of it. It could be a very large and uncomfortable polynomial. But that's the definition. It's not exponential. So one thing I want to keep in mind is I'm making no assumptions about the distribution of examples. I'm making no assumptions about the sequence, any specific sequence. The learner is not getting any help from the teacher by carefully constructing a sequence of examples. There is no curriculum here. The examples could be chosen in an adversarial way, and the only thing that the teacher could be adversarial, or nature could be adversarial, it constructs a difficult set of examples. The only constraint on nature or the teacher is that it's not allowed to change the function after having chosen it in the beginning. It doesn't matter what the sequence is. The game that the learner has to play is the learner gets an unlabeled example. It first commits to a prediction before the true label is revealed, and now after that potentially it's the error. And in the mistake-bound model, we only count the number of mistakes. There are other metrics for quality, but we care about the number of mistakes in this particular setup. I'm going to argue that online learning is a rather intuitive model for learning because it can be instantiated in a wide variety of cases. Imagine there's an assembly line and a robot hand has to make a decision, and every time it makes a mistake, it gets some feedback. This is the assembly line of things that keep coming in. Or you can frame this in the context of language learning. We want to teach a program something about language, and we correct it only when it makes mistakes. It's also another increasingly important class of algorithms for when your data set is so large that you can't even fit it in memory, which means you need to do some sort of streaming of the examples. And in this case, the evaluation of the mistake-bound model is how many mistakes would it have made in a long run, perhaps an infinitely long run. And what I would like you to think about, but maybe not comment on right now, is what connection it has to the real goal of learning. Meaning, does this process give us generalization? Does keeping track of the number of mistakes give us generalization on future examples? If I give you a mistake-bound algorithm, and I'm not going to talk about it, but think about this, and I'm going to argue. I'm not going to tell you the answer. The answer is yes, but think about why that's the case. So, like I said, this is a worst-case model. There is no notion of distribution. There is no memory involved. All the learner can be an extremely simple thing. All it needs is enough memory to store one example, store one prediction, and store the feedback, and the model, of course. It does not need to store the data set, and perhaps it might be too simple. Maybe this could be, if we gave it more memory, it could be doing a few interesting things. And there is another starting point. We don't know a mistake-bound model. Let's say I tell you that I have a mistake-bound algorithm for self-driving car. It can make no more than a small number of examples, not even polynomial. Let's say constant. Let's say I give you a self-driving car learner that will make exactly 10 mistakes. Exactly 10 mistakes, but I'll not tell you when the 10 mistakes happen. Over lifetime, if this car runs till the end of the universe, it will make only 10 mistakes, but it could be when you're standing in front of it. So, the global behavior may not be clear. Was there a hand? Yes?
Let's say you've learned a hypothesis, and then the nature of or an adversary gives you an example that is disjoint from everything you've learned. Do you throw away your hypothesis and form a new one? Or
You need to update your hypothesis, and that's really the internals of the learning algorithm. That is exactly what we have to decide as designers of the learner. We have to decide what the learner has to do when it makes a mistake, how it updates itself, how it updates the hypothesis.
So I'm asking, if you don't update the hypothesis, do you get rid of it if it disjoints?
What do you mean by disjoint?
So you have a hypothesis, and it follows a particular method, but then you have one example that doesn't follow that method.
Oh, I see.
You throw away everything you've learned and learn the new one, or get rid of the example and wait for future.
These are both choices that we have to decide on. Keep in mind, in this case, we are assuming that the true function is fixed. So even though the adversary has the ability to pick instances, it does not have the luxury to change the true function. All this, the fact that there is a new example that seems to have changed everything, all that means is that your current hypothesis was not the true function, which means you can choose to update it, or you could say that there is noise in the system and I'm going to ignore this thing. That's a trade-off that we make.
That was my question,
Yeah.
the noise.
There is going to be noise. For the first part of when we are looking at online learning, or maybe, I guess today we are of course not enough time, but we'll be spending some time looking at the noise-free case, and then we'll get to what happens when noise comes in. Noise is going to be a pain that we'll have to live with, and you could choose to throw away an example, but then that could be a problem in its own. So we need algorithms that are flexible enough. But the advantage of this framework is that it's simple enough that it allows us to do some analysis, and even in this really, really simple game, there are interesting issues that arise. We will be able to prove that some concepts are unlearnable. And it turns out that there are generic methods to convert any mistake-bound or online learning algorithm into an algorithm with generalization guarantees. So if you can invent an algorithm in this setup, it will become it will automatically, you can inject generalization guarantees into that algorithm. One question to think about is counting mistakes enough? Perhaps counting mistakes is too simplistic, because maybe it's the worst case, but maybe let's say that the learner has some arrangement with nature and bribes it. It will giving only repeatedly the same example over and over again, and it remembers that example. If that is the case, maybe it looks like the algorithm is fantastic, but it has only seen one example. So there's some philosophical questions to think about whether learning mistakes is, So there are 6 or 7 minutes left, and I'm going to try to at least introduce a proof of concept mistake bound algorithm called the halving algorithm. Like I said before we get into the standard mistake bound algorithms, namely something like perceptron, you first need to be convinced that such an algorithm can exist. That there are mistake bound algorithms that exist because I've just defined a set of algorithms. Maybe that set is empty. And the answer is this proof of concept algorithm called halving. And halving is a neat thing because you can actually prove interesting things about it, but actually it's impractical. So it's just proof of concept. Let me give you an example. The way I'm going to set up is I'll first define a concept class, a Boolean, and then I'll show you an algorithm which is not a mistake bound algorithm, and then I'll show you a generic mistake bound algorithm for the same concept class. Just to show you that not all algorithms are mistake bound. So let's say that we have a concept class C, and the goal is to learn this function f that's inside C. I'm going to define an algorithm called con, which is short for consistent, and this algorithm is not a mistake bound algorithm, but it's going to learn the function. What you'll do is this learning proceeds in rounds, right? At the ith round, at any point, this algorithm is going to keep a big list, a set, let's say, of every function that is consistent with all the previous examples. When I say consistent, what I mean is all functions in the set Ci would have made the correct prediction on all the I-1 examples that it has seen so far. Okay? The reason this is a proof of concept thing is because you need to keep a list of all functions, which is impractical, but it's a thought exercise, so we can do that. At that point, what you will do is now we play the game. A new example comes in. And what this algorithm does is it picks a random function from Ci and makes a prediction. It pretends that the concept, the hypothesis is some random function from Ci. It makes a prediction, and at that point, the new example is revealed, and it has to remove all functions that did not agree with the label that it just saw. So you could start off with a big set of functions, all of the functions, and then you pick a random function, let's say this one, and you make a prediction. And now you realize that that prediction was wrong, and you need to now you throw away all functions that would have made the wrong prediction, and now your new set is this thing here. New example comes in, you make a prediction using this function, and you realize that maybe it was right or it was wrong. Let's say it was right this time, but there were other functions that were wrong, and you telescope in and you disregard all these things. You keep zeroing in on the true function by deleting functions that were incorrect at each point. What this means is, from this picture, at every iteration, the I+1 concept, the set of functions that are valid, is clearly a subset of the previous set that we just saw. Which means, if it makes a mistake, the number of functions is going to be a strict subset of the previous functions, the number that we saw. Which means the number of functions has gone down. Which means progress is made. There are only a finite number of functions. Which means eventually you'll come to a case where there's only one function that's consistent with everything that we've seen so far, and that one function must have been the true thing. This may seem like a one-headed algorithm, but let's play with it. Clearly, this algorithm, there is one function that we know is going to be consistent, which means it cannot make more than the size of the concept class number of mistakes. Right? Does this make sense? Any questions about the algorithm? Yeah.
So are you saying this is a mistake-bound algorithm, or it's not?
Is this a mistake bound algorithm? That's the question. And I think I'm not going to have time to answer this question yet, but I want you to think about it. Is this a mistake bound algorithm? Now, keep in mind, mistake bound, here are some factors that we can consider when you are thinking about the question. The number of mistakes this algorithm makes is order of the size of the hypothesis of the concept class. A mistake bound algorithm, an algorithm is said to be a mistake bound algorithm if the number of mistakes it makes is polynomial in the dimensionality. Which means you need to relate this quantity here, let me use a different color. You need to relate this quantity here to the dimensionality. If you can show that for a concept class, the number of functions that exist is polynomial in the dimensionality, this algorithm is mistake bound. If not, it's not. So the answer to that question depends on what the concept class is and what you can do with it. I'm going to now stop, but I just want to give you a hint about a review of coming attractions if you want. I'm going to show to you that for any Boolean concept class, we can do better using a different algorithm called halving. Halving is something that is definitely better than this. And if you want to build up the intuition for halving versus this thing, think of this process as searching an array. You can do linear search or you could do binary search. Binary search is definitely better if you have some more information, like the array is sorted. Halving is going to look like binary search, this is going to look like linear search, and let's see if we'll build up on this in the next class. Alright, I'll stop now and look out for a homework that will show up. Yeah, I know.
So the recording for this class is going to show up as one lecture or in two separate files?
One lecture probably, yeah. Huh? 3 files?
Stops every 30 minutes.
Oh, yeah, so you're right.
3 files? Yeah, my God. When are the lectures uploaded usually?
So this will already be available.
The one with the webcam will be available.
How to stop the streaming?
Yeah, I think you need to go to the Wi-Fi.